Hello, everyone. In this presentation, we're going to cover the scientific method, also known as the process of science. So if we look at this chart and we kind of fill in some of the blanks here, probably you're used to thinking of the process of science as it proceeds from left to right on this chart. So think of this chart as consisting of three different columns: a left-hand column, a middle column, and a right-hand column. So if we run this chart from left to right, that's the more traditional way of thinking of the process of science. Where do we begin in that process? Often we go out and we collect sense data, that is, observations about the natural world, or perhaps we perform experiments in a laboratory and we record the results of those experiments. That's perhaps the initial step in the process of science. In the middle step here, what we're doing is taking the data that we collected in step one and analyzing that data in step two. And one of the first things that scientists do when confronted with the data set is they look for patterns, is they try to connect different parts of the data set to one another. That process is all about pattern analysis. In this step, scientists are synthesizing their data. Whatever else that science is, I think we would agree that science is a rational enterprise, meaning that we have to employ the rules of logic when we analyze data and collect data and make sense of our data, because we want to make sure at the end of the day that our conclusions don't collapse into self-contradiction. So rational thought and logic are certainly an important part of doing science in step two. And to me, another part that often gets left out of the equation when discussing the nature of science is that science is inherently a very creative enterprise. In this regard, it shares some similarities with art. So often, it's not just enough to be really good at analyzing data and teasing out patterns. Very often, real progress is made in science when somebody comes along and can look at that same data set that everyone else has been staring at for decades and ask a completely new question of that data, particularly a question that has some hope of being answered. And so we really shouldn't discount the importance of creativity in science. Okay, so if step one is making observations and performing experiments, and step two involves pattern analysis, rational thought, and creativity, then how about step three? Well, step three can be thought of as the so-called output of science, and it involves the construction of both hypotheses and theories. Well, what's a hypothesis? A hypothesis is simply a statement that requires testing. And very often, initially, when we analyze our data, we begin to think of explanations that would explain why it is that these patterns emerge. But at that point, we haven't yet investigated our explanations. And so that explanation, that initial model, if you will, would still be a hypothesis. Eventually, though, and it doesn't happen very often in science, when models or groups of hypotheses, groups of ideas are tested over and over and over again, and no contradictory evidence is found that would allow us to disregard our ideas, and particularly when lots and lots of confirmatory evidence is supportive of these ideas, then very often these models, these hypotheses get raised to the status of what's called a scientific theory. And what do scientists mean by a theory? I'm not going to attempt to define that word. Instead, I'm just going to offer a few characteristics of scientific theories. So fundamentally, a good scientific theory has to be testable. We have to at least be able to imagine some test, some experiment, some observation that, if true, would either confirm or disconfirm, that is, falsify our theory. Scientific theories also do more than just describe the world, they explain it. And in this case, by explaining the world, what I mean is specifying relationships between different data sets. Why do earthquakes occur where they do, for example? Well, as we'll see in this course, plate tectonic theory has a simple and elegant explanation to that question. So in that sense, plate tectonic theory is certainly explanatory. It doesn't just describe earthquakes and volcanoes and the history of life and mountain building. It explains these phenomena in terms of a larger idea for which compelling evidence exists. Also, scientific theories are provisional. What does this mean? It simply means that they're not perfect. They're subject to change without notice. And we'll certainly see this with plate tectonic theory in this course. In the early 1960s, when plate tectonic theory was developed, it was so good that it was essentially universally accepted by all geoscientists within just a few years. Since then, however, in the last 50 years or so, plate tectonic theory has undergone several important upgrades and several important modifications, which we'll talk about in the class. So in that sense, plate tectonic theory, like all other scientific theories, is provisional. It's subject to change. And then perhaps the most important characteristic of all is that scientific theories are predictive. This just means that they can be used as the basis for making risky predictions that we don't know whether or not are true. But at the end of the day, scientific theories act as a guide for helping scientists further explore and investigate the world in ways that they wouldn't be able to without that theory. So we'll get into all of this. A couple other quick points before we move on, and that is that nowadays most science is done collectively. It's done by groups of researchers, and when researchers publish their findings in peer-reviewed scientific journals, that really is only the beginning of the vetting process when it comes to science. And typically, science is no longer done by a single scientist working alone in a laboratory. It's done by an entire community of scientists who are both doing the initial work and reviewing the work of others. That is to say that modern science is very much a communal and a collective enterprise. Well, I want to finish this slide by pointing out this bottom arrow, this yellow arrow. And what I want to emphasize here is that, frankly, the more common way of doing science is not to proceed from 1 to 2 to 3, but to run the scientific process the other way, from 3 to 2 to 1. In this more typical way of doing science, a hypothesis is where you start, or perhaps you start with a fully established scientific theory, and you ask yourself, as a scientist, what are the implications of that theory? What patterns should I be able to detect in the world if this theory is a good one? What observations should I be able to make, or what experimental results should I be able to find if my theory is a good one? And in that sense, a good scientific theory is like a mental map that helps scientists investigate the world and even think of questions to explore that they wouldn't have otherwise thought of without the scientific theory in the first place. So just to summarize this entire slide, 2 important points. Modern science is very much of a collective enterprise. And number 2, it's perhaps more complex than we often give it credit for. We can run the process of science from left to right or from right to left in this diagram. Well, are scientific theories true? Well, that's an interesting question that I'm going to leave you to explore on your own. And I just want to share a quote with you, a famous quote often applied to science by George Box. And Box said, quote, essentially all models are wrong, but some are useful. So what do you think Box meant by that quote? Just some quick background here. Box was actually a statistician, and so the models that Box was talking about actually are statistical models. But a lot of scientists picked up on Box's ideas and applied this quote to the process of science, not just to statistics. So what do you think it can mean to say that all scientific models are wrong, but some are useful?